Igor, we should switch to English.
Yes, I'm about to. Yes, thank you. Okay, so should I start?
Yes, I think so.
Okay, thanks. So I'll be talking about Gröbner fans of flag varieties, and I think I'll just dive into it. So I will start with reminding some simple definitions. So first of all, initial ideals. Here we have what we have in this context. I will have a polynomial ring S in n variables, and what I will choose is a weight. So it is capital N real numbers, one for each variable, and this lets us consider a real grading on the ring S, where the variable xi has grading wi, and then in this setting for any polynomial in S, we have its initial part with respect to w. It's denoted like this, and so what this means is that if we have a grading on the variables, every monomial occurring in P has some grading, some real grading, and out of these we can choose those monomials which have the least occurring grading, and the sum of these monomials will be the initial part. So here this is written as a formula. So here's our polynomial P. The di's, they are some vectors in tuples of n natural numbers, and ci's are coefficients. And then so here's what I said just now. We take those. So the grading of the monomial x to the di'th power, where di is a vector, is the scalar product, because we have wi occurring with coefficient corresponding coordinate of di. So the grading of the monomial is the scalar product, and we choose those for which the scalar product is minimal, and we retain only those monomials. The rest we throw away, and what remains is the initial part. Okay, and why we need this?
So it's not as usual the highest part. So
this is, well, there are two conventions here. The main
so
convention.
you are considering ideal at zero. That's why you choose the minimal. Yes.
Excuse me. No, well, I choose the minimum mostly because that's the setting I usually work with. But there are two, the max convention and the min convention. I mean, they are equivalent, obviously, but there are.
So if it's polynomial of one variable, is the order of zero of the polynomial at zero.
Well,
if it's one,
it depends on the grading. So we choose. It's either.
Okay.
No,
in one variable, as I said, there is.
Yes. So
grading.
For one variable, we will have one real number w. If the number is positive, we will have the monomial with the least power. If it is negative, we'll have the monomial with the largest power, according to this definition. If we use the max convention, then we have to switch this around. Okay, so some contexts use the minimum, some contexts use the maximum. This is really, these are two equivalent languages, and they're easy to switch between. So why I need this is because it's to define initial ideals. So the nice fact about this definition is that if we have any ideal in our polynomial ring, we can do the following. We can take all of its elements, we can take all of their initial parts, and we can take the subspace spanned by these initial parts. And it is easy to check that this subspace will actually be an ideal itself. So, and this is known as the initial ideal of I with respect to the weight W. And okay, and well, here I have some small examples. So we have polynomials in 3 variables, and we have a principal ideal generated by this expression here. Well, and we use this weight here. So, and if you compute the weights of the 3 monomials, you will see that the weights of the first and the last one are 10, and then no, sorry, they are 4, and the weight of the one in the middle is 6. So the initial part is the first one and the last one. And then of course, well, a simple fact is that if we have a principal ideal, the initial ideal is also always principal, and you just have to take the initial part of the generating element and generate an ideal by this initial part. So this is what happened here. We computed this initial ideal of a principal ideal. And well, perhaps some of you, many of you, well, most of you probably who've met initial ideals have met them in a slightly different setting, where they are defined with respect to monomial orders. So where we take all the monomials in the ring and we take a multiplicative ordering of them. And this is, I mean, this, all I want to say is that this definition is actually, it is no less general than the other one. So these are two equivalent definitions. Everything you can obtain via real weights, you can also obtain via monomial orders, and vice versa. I'm not going to give the other definition, but just for those who are more used to it, this is sort of saying that it's the same thing.
Sorry, excuse me, Igor. What means monomial order? Could you repeat, please? Sorry.
Well, I'm not going to be using this definition, but a monomial order on our polynomial ring S. So it is a order. So we take all the monomials, which are, well, the monomials, they are in obvious bijection with the same group natural numbers to the nth power. And so you take a semi-group order on the semi-group. So the order on the monomials has to respect multiplication. And if you have an order like this, you can take a polynomial and say that its initial part are those, well, it can be a partial order. And then you can say that the initial part of a polynomial is the sum of those monomials, which are the least with respect to our monomial order. And this is actually what I did here. This W does define a monomial order, obviously, where we just order all monomials by their weight. But of course, there are other orders. There's, I don't know, lexicographical order and many others. And well, I'm saying that the initial ideals obtained from, well, strictly speaking, weak monomial orders is the same set of initial ideals you can obtain from real weights. Does this answer the question?
Okay, thank you.
Okay. Okay, so let me just, and here is sort of, well, the main reason. This is, well, initial ideals occur in many settings, and they perhaps, I think they stem from computer algebra, but, well, the main reason for me to consider those ideals is this Gröbner degeneration construction. What I want to say is that every initial ideal actually defines, it is in some sense a flat degeneration of the ideal we started with. Okay, so and how this is just a very, I mean, we are not going to be using this, but this is a sort of a very simple and neat construction, which you can really sort of understand. And this is why I'd like to explain this. So in this setting that we had on the previous slide, I'm going to make some assumptions. So I'm going to assume that the ideal is homogeneous in the usual sense. So it's homogeneous with respect to the grading by degrees of polynomials, and I'm going to assume that the coordinates of our weight W are integers. Okay, and now for every polynomial in our polynomial ring, we can define its homogenization. So it's a polynomial where we added one additional variable t. And so what you do is you multiply every monomial in our polynomial by t to the power equal to the grading of this monomial. So again, this scalar product, which is the grading of the monomial x to the power di. And then we take this whole sum that we obtained and we multiply it by a negative power of t, so minus the minimal occurring grading of monomials. Well, and of course, so this is precisely the grading that appeared in the definition of the initial part, and this means that when we multiply by this power, we will only have t to non-negative powers, namely all the monomials that are in the initial part, they will contain t to the power 0, and all other monomials will contain t to some positive power, right? And well, and now the rest, the rest of the slide is actually the idea that now if we take the limit t goes to 0, then all the monomials outside of the initial part vanish, obviously, and what we are left with is the initial part. And so this is a degeneration. So to formalize this,
may I ask, since your claims that you do not say that homogenization of S gives the whole ring S of T. You do not say this, right?
No, I do not say this. I don't think that's true. I mean, but we will not be homogenizing just any polynomials. We'll be specifically homogenizing polynomials in R. So what we do is,
t to the first power does not occur as ph of some p, right?
Sure. I think what is true is that if you take the subspace linearly generated by the homogenizations of all polynomials, it does not generate S as a linear space, but it generates S as a C of T module. So you can multiply by powers of T, and then it will you will obtain the whole ring S of T.
Okay, thank you.
Okay, and yeah, so from this we get the definition of the homogenization of an ideal I. So what we do is we take the homogenizations of all of its elements and we generate an ideal by those homogenizations. And well, yeah, I mean, so what I'm going to say now perhaps is it's not, I mean, exactly obvious, but it's very easy to check that. So basically, when we do this, we consider this homogenization, and then we can specialize T, right? We can set T equal to some complex number, and then we get a map back into S, and then the image of the homogenization of this fancy I, it will be some ideal in S, And well, you can see easily that if we specialize t to 1, then we are back with the ideal I that we started with. And if we set t to some non-zero number, what we obtain is almost the same ideal. So it's only changes. So here you will have, instead of 1, you will have a to some power here. So this is just a change of variables where you multiply every variable by a non-zero constant. So this is what when we specialize t to a non-zero number. And when we, so this is what I said about t going to 0. If we specialize t to 0, then this homogenization specializes precisely to the initial idea, right? And what this means, so we have this ring S of t modulo this quotient ring modulo I, modulo fancy I, and this means that if you specialize, it is a ring over C of t, and if there you can also specialize t, and if we specialize t to a non-zero number, we will have a ring isomorphic to the quotient modulo I, and if we specialize t to 0, then we'll have a ring isomorphic to the quotient of modulo the initial idea. And this means that you can view this, and it is also free and hence flat over the polynomials in T. So what you have is a flat family where the sort of all the non-zero spot, the generic fibers, meaning all fibers except the zero fiber, are S modulo I, and the special fiber, the zero fiber, is S modulo the initial ideal. So you can look at this sort of geometrically. You will have this flat family over the line, over the affine line. And there, so the fiber in 0 the fibers outside of 0 will be the proj or whatever, the algebraic variety defined by the ideal I, and the special fiber, the zero fiber, will be the algebraic variety defined by the initial idea or the proj. And more generally, okay. So, and this is sort of, well, for me at least.
Excuse me. Sure. Do we assume that straight I, Roman I, is homogeneous?
Yes, here at the very beginning.
Yeah. Okay. Okay.
Well, I mean.
Otherwise, proj is not defined again.
Of course, yes, but I mean, algebraically, you can say that. Well, you need to make some assumptions at least. You can say that. You can say something similar when I is not necessarily homogeneous, but then you'll have to make some assumptions, stronger assumptions than W. You'll have to assume, for instance, that W has non-negative coordinates. And here we actually do not require this. But of course, this in some form, this also works for affine varieties, or affine schemes. Okay, and this is sort of, well, for me at least, the main motivation for studying initial ideas, because this is how I sort of, why I started studying them, because they define these flat degenerations. Okay, and now, so what I'm going to talk about today is classifying, well, the initial ideals of an ideal, of a specific ideal. But so how does this work? So the classifying structure here is the Gröbner family. So once again, we are pretty much the same setting. We have an ideal. We again assume it to be homogeneous, and we have some real weight W. And so we have this n-dimensional real space. For every weight in the real space, we have an initial ideal. And it is natural to ask ourselves how this initial ideal depends on the point in the real space. So how does the initial ideal depend on W? And the answer to this question is the Gröbner fan. So let us use the full notation for, so if we have an ideal I and another ideal J, let Cij so is a subset in a real space consisting of those weights for which the corresponding initial ideal of I is equal to J, right? So, I mean, if I and J are just any two ideals, this will likely be an empty set, but well, sometimes when J is the initial ideal of I, this set is non-empty. I will, so throughout the talk, I will sometimes say things like J is an initial ideal of I will mean precisely that the set Cij is non-empty. Okay, and so these are you can view these the non-empty Cijs. You can view them. I mean, if you fix I, they form a partition of a real space, right? TheseCijs, they are disjoint and their union is the whole space, and you can view them as equivalence classes. So if you find an equivalence on points in the real space, 2 points are equivalent when the initial ideal of I is the same. These are the equivalence classes. And now, so in a paper, in an 88 paper, so two Italian, I think they were computer algebraists. So they anyway, they discovered this very nice structure, the Gröbner fan. Namely, so and the main statement here is that all of these equivalence classes, all of these Cijs, they are polyhedral cones in our real space, and well, they're relatively open. I mean, what relatively means, I mean that they're a set in a real space is relatively open if it's an open set in its linear hull, right? So you take the minimal linear space containing this cone, and it has to be open inside inside the space. Yeah, but the main thing is that all of these cones, I mean, there's many cones. They have different dimensions. But the main thing is there is a finite number of different cones. So every ideal has a finite number of initial ideals, and all of these cones, they fit together nicely to form a polyhedral fan. So I mean, I think most people know what a polyhedral fan is. So it means that for these cones, their union is disjoint, and so the face, if we take any cone in our set and we take any of its faces, it also has to be in the fan. So it's a polyhedral complex consisting of cones. Right, so maybe just one, before I list the key properties, I mean, one thing that is completely obvious is that these equivalence classes are sort of cones. I did not write this here, but obviously, if you take W and you multiply it by a positive integer, by any positive number, the grading of any monomial will be multiplied by this same number, and so the initial ideal will not change. So this shows why they are cones in the sense that they're invariant under multiplication by positive numbers. But so why they are polyhedral and why they fit together to form a fan is more tricky. Okay, so but we have this fan, the cones of which parameterize all the initial ideals of our ideal, and so it has well, here's the three main properties that I want to mention. It is so first of all, it's the first thing you have to understand when thinking about this fan is that the cones in this fan are usually not pointed. So here I say that this CII, well, we have CII, so this is the set of W's with respect to which the initial ideal of I is I itself. And this is the minimal cone in our fan. So every other cone, it is a face of every other cone. And right, and then when you sort of think about a conventional polyhedral fan, you always think that the minimal cone is a point, right, and which is the vertex of all the other cones. But this is usually not the case here. So this is CII, the minimal cone in our fan is usually a linear space of positive dimension. So, and it is the apex of every cone. So there is no point. The minimal cone is some linear space of positive dimension. So actually, if I is homogeneous, this is always the case. It always has positive dimension, at least one. Okay, and so this is about the minimal cone, and then what about the maximal cones, right? So when you think about the fan, the first thing that you think about are the maximal cones, which are the largest ones, and so they correspond to monomial ideals. So right, so the idea here is that I will make this precise in a moment, but the idea here is that the more degenerate the ideal, so the less monomials you have retained from every polynomial, the larger the corresponding cone. And so the largest cones in our fan, they correspond to the most degenerate ideals, and those are the monomial ideals, right? So a monomial ideal is an ideal generated by monomials. And well, one obvious thing is that if for instance, any initial ideal of a monomial ideal is equal to this ideal, to the ideal itself. So if I is monomial, then the initial ideal is necessarily equal to I. It cannot be degenerated any further. And so this is why then they are the most degenerate ones, and they correspond precisely. So the monomial initial ideas precisely correspond to the maximal cones. And so this idea about the cone being the larger, the more degenerate the ideal is, this is made precise by this statement here. So consider two initial ideals of I, right? J and J prime. And well, since the cones fit together to form a fan, a natural question is, when is one cone a face of the other cone? And so this is actually, so this happens precisely when J prime, so J prime, the cone corresponding to J prime has the cone corresponding to J as a face, precisely when J prime, the larger one, is more degenerate. And more degenerate means that J prime is itself an initial ideal of J. So we can sort of, if we can degenerate I into J, and then we can degenerate J into J prime, then we have this relation. One is a face of the other. Okay, and here I have some very, very basic example. I mean, better examples would require three-dimensional images, but this is a sort of very basic example here. So we have this principal ideal in polynomials and two variables, just generated by the sum. And so its fan is, so the fan is very simple. I did not draw it because, I mean, it's just a line. It sits in the two-dimensional plane, and it's a line. It consists of the line and two semiplanes on both sides of it. So these are the three cones that occur in the fan. So this line, this line is given by the two coordinates being equal to each other, this sort of diagonal line, it is the cone CII. So what I'm saying is that when W1 is equal to W2, the initial part of x1 plus x2 is x1 plus x2 itself, because both x1 and x2 have the same grading, so they both go into the initial part. Okay, so this is CII, it's a line, and then we have two cases when the two semiplanes when W1 is larger and when W1 is smaller. And these are the two initial ideals. One of them is the ideal generated by X1, and the other one is the ideal generated by X2. So this is sort of very, very simple picture. But of course, in higher dimensions, we have more complicated, and we will see a sort of example later on. Okay, and what?
What is the fan of the maximal ideal?
So if you take these sort of irrelevant,
all generated by xi's.
Yeah, so if the ideal is monomial, it does not have any non-trivial initial ideal. So this is a monomial ideal. It's going to be there's going to be one cone, and this cone is the whole space. So
I see. It's
as simple as it gets.
Yeah, it's clear. Thank you.
Because this is the ideal is as degenerate as it can be. So okay, but well, we are not going to study initial ideals, though. Just any abstract ideals. We are going to talk about one specific ideal I'm interested in. This is the Plucher ideal, which defines the Plucher embedding. So a quick reminder on what that is. So we have an integer and n, and we have the flag variety. So the variety of complete flags in an n-dimensional complex space, right? So a flag is an increasing sequence of subspaces of dimensions 1, 2, so on, n-1, right? And then, well, we all know that this flag variety, it can be embedded into this product of projective spaces, right? The Plucher embedding, where sort of the one-dimensional space in the flag defines the point in this first multiple, the two-dimensional space defines the point in the second multiple, and so on. So that's the Plucher embedding. And well, this is a multi-projective realization of the flag variety, meaning that, so this is a this P is a multi-projective space, meaning that subvarieties, they are given by, it has a multi-homogeneous coordinate ring, which is a polynomial ring. The variables in this ring are the homogeneous coordinates in these projective spaces. So we have n choose 1 coordinates here, n choose 2 coordinates for the second multiple, and so on. So we have, in this multi-homogeneous coordinate ring of this product, we have the coordinates, they are parametrized by subsets, subsets of integers from 1 to n, of sizes between 1 and n-1. So for every such subspace, we have one coordinate. If it has k elements, it is a homogeneous coordinate in the k multiple. Okay, and so this will be our ring S. And subvarieties in this product P, they are defined by, well, multi-homogeneous ideals in this polynomial ring. So there must be some specific ideal corresponding to our subvariety Fn, the flag variety, and this is known as the Plucher ideal, or sometimes the ideal of Plucher relations, right? So this is this. I will just denote I. This is the Plucher ideal. Oh, sorry, this should be S here, but instead of R, I've got to sort of switch between R and S in the middle of writing my slide. Anyway, so we have an ideal, distinguished ideal I, the Plucher ideal, and the quotient S modulo I is known as the Plucher algebra. It is the, well, it is the, so to speak, multi-homogeneous coordinate ring of the flag variety with respect to this multi-projective embedding. Main thing is we have this polynomial ring and we have an ideal there. And well, and going back to what I said about Gröbner degenerations, initial ideals of I, they provide flat degenerations of the flag variety, and this is something that has been studied extensively. There are many different papers which construct various such flat degenerations. Yeah. So here it says by a multi-projective version of the flat family construction. So if you remember here 2 slides ago, here I said proj. Of course, this won't fly in this context. You need to use this multi-proj because we are not working with this is not a projective embedding. This is a multi-projective embedding. But whatever. I mean, on the algebraic level, it's all the same. The quotient is a flat family. And
Igor, excuse me.
sure.
So what geometrically meaning of these degenerations? So
Oh.
flat variety is a subset of increasing sequences of subspaces. And how you see degenerations? What's the geometric object?
Okay, so well, there are many different, as we will see, there are very many different. So every initial ideal defines some degeneration. So if you want to give a description like this, then you have to well, there has to be a separate description for every initial ideal. And well, we know some set of degenerations, we know some explicit constructions, but I would say that for most of them, we do not have a characterization similar to this sequences of subspaces. It's
I'm not insisting on sequences of subspaces. I just want to see any object, because otherwise it's hard to imagine what kind of
well they are. I mean, we are going mostly. This is so this Gröbner fan business. This is mostly actually about classifying the degenerations more than describing them. But of course, there's an equally important problem of describing degenerations. And well, there's many papers that do this, and they're usually, I mean, there's various geometric realizations that, I mean, they're not necessarily model spaces, but for instance, what we are about to see, many of them are like toric varieties or maybe semi-toric varieties. And some of them come from geometric representation theory, so they have some representation theoretic realization as orbit closures.
So there is a list, so to say.
Yes. So
interesting degenerations coming from needs of other theories. Do I understand correctly?
yes. So this is very accurate. So this whole field can be viewed as a sort of assortment of various constructions. And perhaps one interesting problem here is sort of is finding a unifying approach. And this is directly related to the Gröbner fan, because this is the structure that classifies all the degenerations that we have. And of course here in the last bullet point, I say that, well, as far as I know, all known constructions of flat degenerations of a fan have this form. So I mean, abstractly, I'm not aware of a theorem that would say that any flat degeneration of the flag variety necessarily comes from an initial ideal of the Plücker ideal. But, well, we could speculate that there is some theorem of this form because, well, among the multitude of constructions that are known, well, sooner or later, each and every one turns out to be given by an initial ideal of the Plücker. So this is one question I will. I can't say I have. Yeah.
Excuse me. I am not really understanding the word degeneration. The construction makes from one variety makes a family of some other varieties, which is flat.
Yeah. So
what is degenerated?
So a degeneration, yeah, a degeneration is a. Well, I mean, you could give slightly different definitions, but one approach is that you have a family, a flat family. Well, whether you require the family to be flat or not is also a choice. But so you have a family, say, over the affine line, right? Like here, for instance, in the very sort of basic definition, you have a family over the affine line, and then you say let us say that all the fibers outside.
You mean
of
the special fibers are the generations
yes,
of
so the special
generic
fiber
fiber.
is a degeneration of the generic fiber. Then
And
well,
generic is the generic fiber is our initial variety, right?
No, the other way around. So the special fiber, the zero fiber is given by the initial ideal. Well, initial. So yeah, the word initial has two meanings. I try to use original. Our original.
Right, start, please.
Yeah, so the original variety is the generic fiber, and the degenerated variety is the special fiber.
And do you have examples when you can describe in some other way the degeneration of some well-known variety?
So even other not a Gröbner degeneration?
Yeah.
Yeah, this is a no, I do not. And this is a very interesting problem, which I have asked various people.
No single example, right?
Well, the question is if there is an example at all.
What happens if we take just projective space as to start?
Well, I don't know if there is an example where it's not a Gröbner degeneration. I know that there is some papers that claim to construct such examples, but actually, if you look at them carefully, this is not what you want. So, of course, I mean, you could take a Gröbner degeneration and you could apply some, I don't know, linear change of variables, right? And taking initial ideals, taking initial parts is very sensitive to any sort of change of variables. So all the initial part business gets distorted. And so, strictly speaking, a linear change of variables already may give you something which is not a Gröbner degeneration in this precise sense, but this is not very interesting. I mean,
and yet another question: does the degeneration, this Gröbner degeneration, depend on the projective embedding or multi-projective embedding?
I mean, in general, of course, yes. In general, if you have for the same projective variety, you have two different projective embeddings, you will have two different ideals, two different Gröbner fans, two different sets of degenerations. But in this case, all the known degenerations stem from this particular multi-projective embedding. And so the question, to which I do not know the answer, but I think it's a really interesting question, is whether there is a precise mathematical reason for this. I mean, there must be, but I don't know.
But these will be varieties of the same dimension.
Yes.
But as maybe stupid question, are they maybe birationally equivalent or something, or nothing?
No, they don't have to be
okay. And are they diffeomorphic to each other?
Well, no. So usually, if you take a smooth variety,
does flatness imply diffeomorphism?
No. Usually, if you take a smooth variety, the degenerations will be singular.
Singular. Okay.
So it's not diffeomorphic. I mean, as you will see, we'll have I will discuss various degenerations.
Yeah, if probably degeneration would not be singular, it would be isomorphic to the generic fiber, right? Or not? I don't know. That's a question.
I don't know. I mean, yeah, I think. Well, I cannot give you really
Okay. Sorry.
Survey of what happens
in a couple of slides.
We'll have different examples, and they're all singular. So, yes, there is. So the lack of singularities probably means something's not right. So we're not degenerating enough. But.
Incomplete flag varieties can be obtained as a certain degenerations of complete flag.
But no, they have a different dimension. But
yes, no, but you said that all degenerations are of the same dimension.
No, yes. But all degenerations of a given variety, flat degeneration, have the same dimension as the original variety. But so if you if you take a partial flag variety, then it has a different. Am I understanding the question correctly? You're asking about partial flag varieties like Grossmanians.
Yes, yes.
But they have a different dimension. So I'm saying that, for instance, a Grossmanian cannot be there is no obvious way for a Grossmanian to be a flat degeneration of a complete flag variety, because generally speaking, they have different dimensions. Of course, you could find situations where a flag variety has the same variety as a Grossmanian, but
no, I'm just thinking about the space which contains the subspace may degenerate to this subspace in certain sense. That's why I just wonder if this type of degeneration, when you lose the dimension of the space, subspace, that can be, you can imagine that on the level of ideals, I don't see why not. Why it's not impossible. But okay, sorry for interrupting.
May I comment here? So I just want to say that then you degenerate something, then the dimension can only go higher, can go up. So you can't move data, but you can add something.
Okay, thank you.
No, but I mean, if you degenerate flatly, the whole dimension will not actually change. If you degenerate non-flatly, defining non-flat degenerations is a sort of
then everything can happen, of course.
Yeah, because this is a very general definition.
Why do you consider only projective varieties, not affine ones?
Oh no, that's the same. Most of the same things can be said about affine varieties. I'm particularly interested in it.
Then I would like to ask, just quadratic curve degenerates to two components lines. Is it a Gröbner degeneration?
So probably yes. So an irreducible variety degenerating into reducible varieties is a very common occurrence that happens all the time.
And what if I ask, if you consider
maybe that answers Roma's question.
Sorry?
Well, Roma asked a question in the chat.
Okay.
Maybe that answers his question, because there's nothing surprising about the degeneration being reducible. This happens. Yes, and you were saying. So I have quite a bit of slides to go here. But maybe
can I still ask?
Okay, sure.
I'm sorry. Last question, I promise.
Okay.
If we consider coadjoint orbits of the complex
the what orbits?
The complex coadjoint orbits, then we have a generic orbit and the nilpotent one. Is it a Gröbner degeneration?
Which variety are you talking? The what orbits?
If you consider coadjoint orbits.
Oh, coadjoint orbits, sure.
I think they have different dimensions.
Yeah, I think.
Dimensions.
I don't. Well, strictly speaking, I don't know, but.
Okay, sorry. It's just.
Okay, let's just leave it at that. I don't know. I think.
I was asking just to feel.
I'm pretty sure the answer is no, because otherwise, that would be an example of flat degeneration. So I'm pretty sure the answer is no, but I cannot give a. Perhaps, yeah, maybe
the generic orbit is just the pair of flags in general position.
Yeah, but that has a greater dimension.
Sorry?
Yeah, but that has greater dimension.
Just not compact, not projective.
No. They are fine. Affine manifolds.
They are fine, not
yeah, but
not fit to our discussion.
Igor told us that the affine are also good. Okay.
Oh, I meant that so you can describe a similar setting for the generations of affine schemes degenerating into affine schemes. This all works very similarly.
Okay.
But in terms of the Gröbner degeneration construction, projective varieties degenerating into affine varieties does not really make a lot of sense. Okay. So yeah, and as you could have guessed, what I'm interested in is, what I wanted to discuss is the polyhedral fan. So the Gröbner fan of the Plucher ideal. I defined an ideal, and I'm interested in its Gröbner fan because its cones classify the, well, certain Gröbner degenerations of the initial ideal of the Plucher ideal. Okay, this is what the very sort of basic observations we can make here. It is a I mean, we have 2 to the nth minus 2 coordinates in the Plucher coordinates. So the fan lives in a real space of this dimension. And well, one thing we can understand easily is how the minimal cone, so this sort of linearity space, how that works. Because obviously, I mean, so let us take a real number a for every k from 1 to n minus 1, and then we say that sort of the for our weight, all the coordinates of our weight, they correspond to the Plucher variables, right? To the variables in the ring, and let us say all the coordinates of our weight with the same number of subscripts are the same. Okay, and then you can easily see then the initial ideal of I will be I itself. This is simply because, so I it defines a subvariety in this product, so it has to be multi-homogeneous, and this precisely means that it is homogeneous with respect to this grading, and so these multi-homogeneous polynomials, they will be their own initial points. Okay, this is easy to check, and then there's another way of constructing weights which have the same property. Namely, you can take a real number for every number from 1 to n, and you can say that, let us consider a weight where this coordinate with subscripts i1, ik is equal to the sum of the corresponding b's, right? And then so, well, it turns out that then again the initial ideal of I will be I itself, because, well, I will not go into too much detail on this, but this is because I is also homogeneous to another n-dimensional grading, which is given by the action of the maximal torus and GLN. So this is actually this n-dimensional grading. Okay, and what I want to say is, so we have, so this second bullet point gives some linear subspace of weights, and this third bullet point also gives some other linear space of weights. And I want to say that CII, the minimal cone in our fan, is actually the sum of these two subspaces. So weights of this form plus weights of this form generate this linear space. Well, this is just an observation, something that we can say right away about the Gröbner fan of the Plucher ideal. And now, well, let us look so at the sort of minimal non-trivial case when so the 3-dimensional flag variety of flags in dimension 3, and so it is a principal ideal, as it is the Plucher ideal is a principal ideal. It is generated by this expression here, and so this is, I mean, you can easily see that it has 3 initial ideals. So its initial ideals are the initial monomial ideals, are the ideals generated by each of those 3 monomials which occur in this expression. And as I said a couple of slides ago, the maximal cones correspond to initial monomial ideals. So we'll have only 3 maximal cones, and there is So well, I have a picture here of how this, Gröbner fan, what it looks like. I mean, actually we have 6 variables here, right? So it lives in dimension 6. But as I said, so we have this linearity space, CII. It is a 4-dimensional space, which is actually it is generated by these 4 coordinates. It's 4-dimensional space. And so we may consider the corresponding section. It will be a 2-dimensional section of a 6-dimensional fan. And I'm saying that actually outside of these 2 dimensions, nothing interesting happens. It is a product of the fan that we have here on this picture and of a 4-dimensional linear space. Just multiply this by a linear space and you have Gröbner fan. And well, here I have all the initial ideals written down. So here we have the, so we have the 3 monomial initial ideals, and then we have the 3 initial ideals, which are less degenerate. So they're generated by principal ideals generated by monomials, and well, we'll actually, I hope to say a couple of words about those. They are actually toric degenerations. And then we have, well, I have not written down, we have another, so the point here, this corresponds to the, this is CII itself. So this is the initial ideal that is I itself. Okay, so this is the Gröbner fan of the 3-dimensional flag variety, and this is very simple. But for n equal to 4, things go completely out of control. And so I just, well, you can do, there's software to compute Gröbner fans, and you can compute the Gröbner fan for n equal to 4. Well, it's an ideal in the polynomial ring in 14 variables, so 16 minus 2. And it is generated by 10 quadratic polynomials. But then if you compute the Gröbner fan, well, I mean, if you apply the software, then it will tell you that it actually has 40,000 something maximal cones, so cones of dimension 14. So it has 40,000 different initial monomial ideals. And well, this is crazy. Compared to the number of ideals that we can actually describe explicitly, this is a very large number. And well, this is, I mean, tangentially related to, here I say that general classification, so sort of general descriptions, exhaustive descriptions of the Gröbner fan seem to be, well, I don't know, they seem to be out of reach. I cannot think of a method that would, at the moment, something that would work here. But what we can do, so we can look for specific degenerations of the flag variety, look at the corresponding initial ideals, and we can describe the corresponding cones in the Gröbner fan. So as far as the structure of the Gröbner fan goes, we can find specific cones and we can give descriptions of those cones. And then, well, this can actually help us find new degenerations. So maybe I will mention how this works, why this works both ways. But okay, so, and the first thing I'm going to discuss are cones corresponding to toric degenerations. I mean, maybe because this was the first thing that was first considered chronologically. So, so what I mean here is that some initial ideals of the Plücker ideal, they can be toric, right? So a toric ideal is an ideal that is generated by binomials and which is prime. But so it is the same thing as an ideal defining a projective toric variety. And so the various toric initial ideals, they correspond to toric degenerations of the flag variety, something which has been studied a lot. And so here is the historically first and best known example of an initial toric ideal. So you can take any two Plucker variables, so with k subscripts and l subscripts, and assume that k is no less than l, and then you can take their product, and you can take another product with sort of I have it written down here, but what we do is we go through the first L subscripts in both of them, and for one variable we write down the maximal one, and in the second variable we write down the minimal one, right? And then for in the minimal part we top it off with the last k minus l subscripts of the first variable. So this is, I mean, for any two Plucker variables, you have this binomial quadratic expression. And if you take all of them for all pairs of Plucker variables, they degenerate an ideal.
Igor, sorry.
Sure.
It looks so artificial. What was the motivation first to introduce such an ideal?
So the goal of, well, this, so here,
the
goal,
who invented it came to the idea. It's
Gunchor, and Lakshmi. So this is the next bullet point. So this was constructed in a 96 paper by Gunchor and Lakshmi. And the goal of this, well, I'm not sure I can say what exactly led them to this discovery, but the goal of the paper is to construct the sort of first explicit toric degeneration of the flag variety. And I mean, of course, this goes slightly back. This is not the very first. They were not the very first to think about this. Sturmfels has some slightly earlier works where he does almost the same thing for the Grassmannian case, the simpler Grassmannian case. But here in this paper, they were constructing toric degenerations of flag variety, and then of some Schubert varieties, and maybe of some Grassmannians.
So I can give a comment here that I think the first, instance, the first kind of paper on this was by Baterev and some other people who were doing mirror symmetry for Grassmannian. They were degenerating, giving some concrete particular examples for degenerations of Grassmannians, and then computing some, some quantities related to Grassmannians and to these degenerations. And this was important for their mirror constructions. And I think Lakshmi Bai and Conchile, they got interested in this subject because of these papers by Baterev and co-authors.
Yeah, it could be, but the Grassmannian, as I said, the Grassmannian case, it predates this Conchile Lakshmi Bai case paper by like 5 or 6 years. So it was in the I think in the very late 80s or the very early 90s, Sturmfels he covered the Grassmannian case, and then so this was okay. Well, no, if by artificial you said artificial. So if by artificial you mean this expression here, then I have to agree.
No, you see what I said is just choose maximum indices for the first group.
Yes.
Minimal for the second.
Very artificial. I agree.
This is for me, who is not expert in the field. It's
yes, I agree. No, I agree. This looks very artificial. Absolutely. This is. I only wrote this way because, well, I mean, I have limited time, so this is a very short way of defining this initial ideal. Of course, I mean, it's nature. It can be nicely described in terms of order theory. So this is actually, this is what is known as the Hebe ideal of a particular distributive lattice. So you can, if you go into the theory or go into the theory of distributive lattices, I mean, you have a certain for every flag variety, you have a certain distributive lattice, which is what you can define in terms of semi-standard tableaus or something. And yeah, so in this, the elements of the lattice are Plücker variables. And then for these Plücker variables, this is precisely their join, and the second one is their meet. So this is just one element of the lattice times another element of the lattice minus their meet times their join, and this is a very general construction. And this ideal is known as the Hebe ideal of the distributive lattice, and its toric variety is something which is well known. It is the toric variety of the
No,
polytope. So
you
this has, yeah.
partly answered the question how it came to birth.
Okay, so this has a very natural interpretation. I cannot explain this. What it has a very natural interpretation in terms of order theory, for instance. And this is the language that Gonchole and Lakshmibai use. And then there was a second paper about this very same toric degeneration, well, and some other things, by Coggan Miller. Well, as you see quite a bit later, and they did not use the language of order theory. They used some other language of matrix Schubert varieties, but they discovered one very interesting property of this variety, and this is of this toric degeneration, that it is actually not. It was known that it is a toric variety, but they found out that it is actually the toric variety of a very well-known polytope, the Gelfand-Zetlin polytope. And I have it just because this is a simple and very nice definition. I have it written down here what the Gelfand-Zetlin polytope is. I mean, I won't go into much detail, but you take a number triangle. So it lives in n-choose two-dimensional space. So here, and these n-choose two coordinates, they can sort of be fitted into a number triangle, where the top row are the integers from n minus 1 to 0, and then all the other coordinates have to satisfy these inequalities. And because they satisfy a finite set of linear inequalities, they form a convex polytope in this real space, and this is known as the Gelfand-Zetlin. Well, of course, we can change the numbers in the top row, but this will not affect the toric variety. They will all have the same normal fan. They will all be strongly combinatorially equivalent. So the Gonchole-Lakshmibai degeneration is the toric variety associated with this particular polytope that you see here. Well, for n equals 4, and this is obviously generalized to larger n. Okay, and then and if in particular, since we know that this toric ideal is initial ideal of I, we can ask ourselves what the corresponding cone in the Gröbner in the Gröbner fan is. So which weights will give this particular degeneration? And so, well, the answer is, I mean, it's a monomial ideal, so it's not a monomial. It is not maximal. This is not a maximal cone, but it is some cone. And its structure, the structure of this cone is very simple, actually. It is the product of this linearity space that we always have, and of a simplicial cone. So essentially it's a simplicial cone. Linear space times simplicial cone. And and so yeah, I have this paper where this is described, and yeah, maybe I'll just say a couple of words about this in the next slide. But yeah, there is another similar. Well, when it comes to degenerations of flag varieties, I mean, there are various constructions, but most of them are pretty abstract. And this Gelfand-Zetlin polytope, Gelfand-Zetlin degeneration, it is nice in the sense that it is very explicit. We can write down the ideal, we can write down the polytope very explicitly. And there's perhaps just one more, well, at the moment, just one other toric degeneration of the flag variety, which is as explicit. And this is so the toric variety associated with the Fagan-Fourier-Littleman-Weinberg polytope, or usually called the FFLV polytope. So this was proved by Zhenya and Ghislain and Peter Littleman quite a while ago. They discovered this polytope, and then later they proved that it also provides a toric degeneration of the flag variety in 2 separate papers. I mean, I will not write down, I did not write down this, how the ideal, the binomials that generate this ideal, but there is some initial ideal, which is also generated by binomials, which we could write down explicitly, which defines a toric variety, which, and this binomial ideal, this toric ideal, is an initial ideal of I. And again, so, well, here I have, just very briefly, this is also a very nice definition of the corresponding polytope, so you could sort of get a feel for what kind of toric variety I'm talking about. Well, once again, so the coordinates it lives obviously in the real space of the same dimension, and the coordinates live in a number triangle. But this time the restrictions are very different. So the top row is again the same, but the restrictions are that all the coordinates are, well, on one hand they're non-negative, and then we limit the sums of various coordinates. So the idea is that you can take any dig path in this triangle, so something that starts in the top row, goes somehow like this, and ends in the top row, and then you limit the sum of the corresponding coordinates by the difference of the 2 numbers in the top row. I will not talk about this too much, but this is how this polytope looks like. It's really pretty neat. I mean, it's more complicated than the Gelfand-Zetlin polytope, but it's also nice. And so yeah. So, and it also provides a toric degeneration, and its ideal is an initial ideal of the Plucker ideal. And well, for certain reasons, this was actually we described this before the Gelfand-Zetlin ideal because so there we have this paper with Xinfan and Zhenya and Ghislain Fourier, where we characterize, well, among other things, we describe this fan, this cone in the Gröbner fan, which corresponds to this toric ideal. And this was actually, I think, the very first time, the very first explicit description of a cone in this fan. So, well, here I say a few more things about these toric degenerations. I mean, actually, maybe just to put this into context, these 2 works, I mean, both of them, they give descriptions of certain cones in the Gröbner fan, but this is sort of a side result in both of the papers. Actually, both papers, they are concerned with certain representation theoretic questions. And, well, to be very brief, how is this related to representation theory? So we have a natural action of an n-1 dimensional torus on the ring. Well, because simply, if you have a product of n-1 projected spaces, it is always acted upon by n-1 dimensional torus. You can multiply all the coordinates in one of the multiples by the same number. So we have a natural action of the torus. And so the ring is acted upon by the torus, and obviously the ideal, it is multi-homogeneous, it is invariant under this action. So this means we have an action of the torus on our Plucker algebra, on the coordinate ring of the flag variety. And if we have a torus action, we have, well, a torus action is the same as a grading, an integer grading on the ring. So we have is the direct sum of its homogeneous components with respect to this torus action. And actually, and these homogeneous components of the Plucker algebra, they're the duals of the finite dimensionally reducible representations of SLN. So they are actually, if you look carefully, they are enumerated by the same objects. So the dual of every finite dimensional irreducible representation occurs exactly once among these homogeneous components. And this is the relation to representation theory here, because now if we have an initial ideal, J, any initial ideal of I, it is also invariant under the torus action, and this means that the quotient ring will also have homogeneous components, and because it is an initial ideal, these homogeneous components, they have to have the same dimensions. Well, and so I mean, obviously this is a very sort of imprecise definition, but it turns out that when we are within these two cones, so when we are either we have a point in this cone, well, or in the closure of this cone, or we have a point in the closure of this cone, it turns out that these homogeneous components of this sort of degenerate Plucker algebra, they can actually, so they are sort of what is known as PBW degenerate representations. So they are sort of duals of PBW degenerations. They are obtained from usual, you can take a representation, a highest weight representation, you define a certain representation theoretic filtration, you take an associated graded space, and well, this is known as a PBW degeneration, and these homogeneous components, they have this form. And so these two papers that we wrote about the Gelfand-Settler degenerations and the FFLV degenerations, they actually study some classes, certain classes of PBW degenerate representations, and then as an application, we obtain descriptions of cones in the Gröbner fan. And just, yeah, is this sort of other questions about this? Because I mean, I understand this is a sort of very hand-waving definition here, but if someone's interested, I could make it more precise. I mean, I don't have that much time left, but that's also something interesting I could talk about. But or instead, I could say that so this is actually related to tropical geometry, because one way of viewing the tropicalization of an algebraic variety is actually saying that the tropicalization, the tropical variety, is a subfan in the Gröbner fan, right? So in our specific case, what is the tropical flag variety, or the tropicalization of the flag variety with respect to the trivial valuation? It is just a subfan in the Gröbner fan. So each cone in the Gröbner fan corresponds to an initial ideal. And then we can consider those initial ideals which do not contain any monomials. Well, this seems to be, this, well, it is some restriction. It defines it is easily seen that it defines a subfan of the Gröbner fan. And this subfan is our tropical flag variety, or maybe the subfan module of the linearity space. And why I'm saying this is because, so these two cones that were described in these papers, they are not maximal in the Gröbner fan, but they are maximal in the cones in the tropical flag variety. And so this is why they're interesting, because they describe the structure of the tropicalization. Okay. But yeah, so the last thing I'm going to talk about is, well, we described certain cones in the Gröbner fan or at least I said that they can be described. But these are not maximal cones. And when you think about a fan, what you really want to describe are the maximal cones which fit together to form the fan. And as I said, these maximal cones, they correspond to an initial monomial ideal. And the question is, well, to describe some maximal cone, we'll have to find some initial monomial ideal of the Plücker ideal. And what I want to say is that there isn't actually a initial monomial ideal that, well, most of you know to some extent. I mean, it is related to a very classical fact, namely that, let us recall the definition of a semi-standard Young tableau. So a Young tableau, well, here I have the definition. So if it has columns, so if this is the jth column, then what it says here is that the numbers, they have to increase strictly down the column, and they have to increase non-strictly to the right in every row. So here I have some examples, right? So here you can see that in every column the numbers increase strictly, and in every row they increase non-strictly. And so this is a semi-standard Young tableau. So this is a Young diagram. A Young tableau is a Young diagram where we have a num in every cell. And then this here is not semi-standard, right? Because here in this column, they are not strictly increasing. Okay, so I hope this makes sense. And there is sort of a classical, absolutely classical result due to Hodge, probably, or something, that so let us consider all products of Plücker variables such that if we take the corresponding subscripts and turn them into Young tableaus, we take all the products such that the corresponding Young tableau is semi-standard. So for each monomial, you have a Young tableau, and it can be semi-standard or not. And those, let us say that those for which it is semi-standard are standard monomials. And what I'm saying is that this is actually a basis. The standard monomials, they form a basis in the Plücker algebra. If you take the natural projection from S to S moduli, they project into a basis. And then, so I think many of you came across this statement. It is very old. And you can actually, what I'm saying is that you can actually look at this classical fact from the viewpoint of Gröbner theory, from the viewpoint of initial ideals, right? So why? Because, well, here I defined the standard monomials in our ring S, and what you can do is you can consider all other monomials, so all the non-standard monomials, and so the non-standard monomials, they span a monomial ideal. This is something you have to check, but it is very easy to check that the linear span will indeed be an ideal. And it turns out that, well, you can show that this ideal, this monomial ideal, is an initial ideal over Plücker ideal. And this implies this classical fact, because so always when we have an ideal and we have a initial monomial ideal, it is always true that the monomials outside the initial monomial ideal form a basis in the quotient. So this is a general property. This is not obvious, but it's very simple. And so a way of proving this classical fact is actually proving this statement about initial ideals and deducing it. But for us, the main thing here is that we have actually found a monomial ideal, an initial monomial ideal of the Plücker ideal. And this means that this monomial ideal corresponds to a maximal cone in our Gröbner plan. So this this C here, this cone here must be maximal. And the question is, how do you describe this? How do you describe this cone? So what are the weights that with respect to which the initial ideal of y is equal to this monomial ideal given by semi-standard tableaus? And well, there is, of course, I will not give description, but this, so this maximal cone can be described explicitly in terms of, inequalities. You can find all of its facets. And so here I just wrote the number of facets. It is this, pretty large number. And the main point here is that, when we had the descriptions of these cones corresponding to toric degenerations, their structure was very simple. They were the product of a simplicial cone and of a linear space. And here this is not true at all anymore. So these are really complicated fans. So we know their facets, but we do not really know what their face lattice looks like. I mean, this is something. Well, I will maybe say about this. So yeah, so I don't know how much more time do I have. So I end at 1/2 right?
Yes, but can you just make a point?
Yes, sure. I'm just sort of estimating what else I'm going to say. So, for instance, here, so we have this characterization of this maximal cone in the Gröbner fan, right? We know its facets. It's an explicit description, but
Igor, I always
Yes.
see such a huge number. I feel hopeless.
Yes.
So
do I.
what does it mean? We know exactly. How you know exactly 2 to the power n minus 5?
Well, of course, I mean, there is some combinatorial. This is just something I can write down simply without going into a whole lot of order theory and distributive lattices. So as I already mentioned, we have a certain distributive lattice here, and these faces, they are parametrized by certain pairs of elements in this distributive lattice. And I mean, you can count the number of pairs explicitly, and it will be equal to this number. But of course, that's not the gist of it. It's just a number to show that the cone is complicated. But it is complicated, and this actually has certain upsides, because I mean, since it's complicated, it has a lot of different faces, and each of those faces corresponds to some Gröbner degeneration of the flag variety. And so one thing you can do now is you can sort of look at this cone, you can find various faces, and you can try to say what the corresponding Gröbner degeneration of the flag variety will look like. And we actually did this to some extent. So here here I say that, we have this large cone, and then we have this smaller cone, which was described a couple of slides ago, which has a smaller dimension, and you can actually show that one cone is a face of the other cone. This means that actually the monomial ideal is an initial ideal of the toric ideal. These are equivalent statements. And then so we have the large cone, and we have a face of it, which corresponds to the toric degeneration. And then, as I said, so all the faces which sit inside the smaller cone, the toric one, the corresponding degenerations were described in these papers about degenerate representations. But then we can go upwards from this face. So we can consider all the faces that contain this toric face. So all further degenerations of the toric degeneration. And me and well, Zhenya Fagin, we have written, well, we have characterized those, actually, we have described them, what those look like. These are, well, they are semi-toric, so they are, this is kind of, well, this is specifically this bullet point here. So all of these degenerations are semi-toric. So this means that their irreducible components are toric varieties, and this is actually has a very nice combinatorial structure, where so you take the Gelfand settling polytope, and you consider what is called a regular subdivision of this. So Gelfand, Kapranov, and Zelevinsky, they have this notion of regular subdivisions of polytopes, and it turns out that you can take the Gelfand settling polytope, you take a certain, well, polyhedral subdivision, and you take the parts of the subdivision and you consider the corresponding toric varieties, and it turns out that they make up a toric degeneration, a Gröbner degeneration of the flag variety when you subdivide the Gelfand settling polytope in a certain way. So all of these intermediate degenerations are characterized in this fashion. Okay, yeah, and then, well, I had another slide here about how we have also another monomial ideal, well, about which is given by PBW semi-standard tableau, and but of course I will not provide the details here. But there is another maximal cone that we can describe, that has been described, and then presumably we can also describe the further degenerations in the same fashion by subdividing the FFLV polytope. This should also provide semi-toric degenerations. Yeah, but these were only the phases that are either contained in the toric phase or that contain the toric phase, and then there's a whole lot of phases which are in neither of the two classes, and of course describing these degenerations is a whole different problem. But this is something that should be done probably. There's a Roma is asking. You mean? I'm not sure I understand what post it is.
You mentioned some
Distributive lattice, right?
Yeah.
So this is this distribute. I mean, this whole area is sort of, there's many relations to order theory. You have partially ordered sets and distributive lattices appearing left and right, but the particular distributive lattice I was talking about, so the elements of this lattice are Plücker variables. So it is not directly related to any fan or polytope. The elements are Plücker variables.
Well, just like to the element in the lattice.
2 to the nth minus 2 elements, right?
Oh wait, but I thought if you take -2, it's no longer going to be a lattice, because I thought.
No. Look, so you're saying that there's a Boolean lattice which has 2 to the nth elements, right?
Yeah.
Yes, but then there's another lattice. It has the same number of elements, but it's a completely different lattice. So it is not the Boolean lattice. I can show you. Well, maybe as sort of last thing, I can show you a picture of this lattice. Whoa. Where is this?
I thought that there is a theorem that any finite distributed lattice is a lattice of ideas in a process.
Yes. So this is the sort of Birkhoff's representation theorem that every finite distributive lattice is embedded into a Boolean lattice. Yes, but it doesn't have to be isomorphic. I mean,
I'm saying it's isomorphic to lattice of ideas inside the process.
can you see this?
Yeah.
Can you see this PDF file?
Yes, we can.
Right. So here I have. So this is the paper. This is the paper that I referenced. So here we have. It's very long. So here, yeah, here. So you can. So here, so here's the Hasse diagram. So right now I'm interested in the left picture. So this is the distributive lattice I meant. I mean, so for instance, the toric ideal, the Guncho-Lakshmi-Bai degeneration, the toric ideal is the Hebe ideal of this lattice. So you take two elements, and you take their meet and their join, and you subtract one from the other. So it is actually obtained from this lattice here. And as you can see, it has 14 elements, but it's not the Boolean lattice at all. And then this is something else. This is relating to PBW semi-standardness.
Is it true that any distributed lattice is obtained from a process?
Yeah, so these, of course, this can be embedded into a Boolean lattice, but this will be a very large Boolean lattice. It will have Boolean lattice with 2 to the n plus 1 choose 2 elements. So 2 to a quadratic polynomial in n.
I'm not saying embedded. I'm saying there is a property of the lattice which guarantees that it is isomorphic to lattice
of ideals, right? So yeah. So this, yeah, good point. So this lattice is the lattice of ideals in what poset, right? So I have this poset. Just one moment. I have it for you here. Okay, so here, well, you take a poset like this, right? This is for n equal to 4. You have it is almost like this triangle we had in the Gaussian photo, but it's slightly different. And you look at this poset, and you consider the order ideals in this poset, and they correspond.
So the order ideas, they are. Yeah, they are.
Order ideals correspond to elements of the lattice.
They are a bit like young diagrams. Maybe half a young diagram.
So yeah, so yes. So I mean, I don't know if I can go into this right now, but if you look into a weakly increasing sequence in this lattice is precisely the same thing as a semi-standard tableau. So this order relation, it is defined by the notion of semi-standardness.
Yeah.
Right?
Yeah.
and then you can look.
Yeah.
Yeah, so this is actually, so this is a very natural lattice, and this is what Gunchuli and Lakshmibai considered
This is
in their paper.
basically something like an order on young diagrams such that the cats are
Yeah, so to obtain the young below, you have to like take this element, write it down as a column, take the next element, take it down, write it down as a column, and so on.
yeah, that-
Any more questions?
mhm. Mhm.
Okay, probably it's time to say thanks for the speaker. If there are no more questions, and okay, thank you.
Thank you.
Thank you.
Goodbye.
Mhm.